In the previous video, we talked about the definition of the specific heat and the molar specific heat. And now we want to look at how physicists, especially turn century, use this as a way to test kinetic theory and to test our understanding of the forces involved at the atomic level. Remember that the total internal energy of a gas we found earlier was equal to 3/2 NKT, and that the energy per molecule was 3/2 kT. Now you can also write that in terms of moles as 3/2 the number of moles times the ideal gas constant times the temperature. By the way, both of those tend to be things that can be asked on the AP exam. So this is the total internal energy. Physicists tend to think about it by adding up each one of the atoms, n of them, and each one has 3/2 kT. The other way to think about it is each mole. So if you want to talk about the energy per mole, the energy per mole is 3/2 RT. So this is the number of moles times the energy per mole, 3/2 RT. So if you know the temperature and you know the number of moles or number of atoms, you know the total energy. Now, let's go ahead and take a look at what we do if we add Q units of energy by heating. If we add Q units of energy to our system, then we're going to change our internal energy of our system. And what is that going to do? Well, that's going to change it by 3/2 in R delta T, or if you prefer, 3/2 in K delta T. Now, this one is the one I want to look at because I want to look at the molar specific heat, which is in terms of moles. So if we compare that to our previous work, we have that Q is little c times N times delta T, but we just said that this is equal to 3/2 R times N delta T. And this says that the specific heat, which we usually say is at constant volume, this is because we want all of our energy that we put in to go into raising the internal energy and not to be lost by some other process. If you have it at the volume changes, we'll find out later it can do work, and some of the energy doesn't go to the internal energy like I've assumed here. It goes to other things. It goes to do work. But if we do this, that C has to equal that 3/2 R. So that means that any ideal gas should require 3/2 of the ideal gas constant to raise 1 mole of gas 1 degree C. And this is in fact what was found when they measured this. Again, this all comes from the idea that we're treating these as free particles moving around in straight line trajectories unless they collide, that the collisions are elastic. This tells us that our model of what's going at the atomic world is correct. So by measuring this, I can then create a model with certain forces and see if I can recreate it. And if I can, it tells me that my model of the forces is correct. This is how we figure out models for things that we do not know or cannot see. We're still doing that today, except now we're looking for things like the Higgs boson. Now, there is a theorem here known as the equipartition theorem. And it says the following. It says, interestingly enough, is what is this 3 and why is it coming about? And it says what happens is that nature is incredibly democratic. When you have an amount of energy and you can store it in some mode that depends on the square of a spatial component, like 1/2 kx squared for a spring, or the square of a velocity component, like 1/2 mvx squared, the square of the x component, then that component will get an amount of energy equal to 1/2 k times t. So this is the energy per mode per molecule. So what I'm saying is if you have something like 1/2 mv squared, that was 1/2 mvx squared, 1/2 mvy squared, plus 1/2 mvz squared. There were 3 ways it could store energy on average. It could store it in the x, the y, or the z. And nature stores equally in all 3 bank accounts. It stores half a kT in this one, half a kT in that one, and half a kT in this one for each molecule. And that's where the 3/2 in kT came from. There was a 3 because there were 3 ways the particle could move. Had it been restricted to only 2 dimensions, we wouldn't have got a 3/2 in kT. We'd have just got a 2/2 or in kT. Now another way of expressing that's usually done is to express the theorem this way. That the internal energy is equal to F times N times 1/2 kT. Or that the energy per molecule is F times 1/2 kT. This F is called the degrees of freedom. And it has to do with the number of bank accounts. So I want you to think of this kind of like you had a robbery, and the robber had 5 people, and each one had only 1 bank account, and you took $100 and you wanted to evenly distribute the money. Then each bank person that was in the heist would get $20. 20 is a measure of temperature. Temperature measures how much is in a bank account. But if each person had 3 bank accounts, or let's say maybe 2 bank accounts to make the math easier, and I still have my $100, and I still had, say, 5 people, so 5 people were involved, but now I have 2 bank accounts each. Then what would happen is this. You would bake this up and put $10 in each bank account. You wouldn't put 20 in one and 0 in the other. You would put 10 in each one. And so the average height now is $10. And so the temperature would only be half as high, as the dollars are only half as high as they were before when they only had 1 way to store the energy. Another way of looking at it is it takes a lot more energy to fill up all of these bank accounts if there are more different ways that the energy can be broken up and divided. So temperature is a measure of this height here. It depends on the number, but it's also depending on the number of degrees of freedom and how much the total energy can be broken up. So you can change the number of degrees of freedom even though you give it energy and not raise the temperature. We'll come back to that with the idea of phase change later on. Let's take the case of the monatomic gas. We've already talked about that. In this case, there are 3 degrees of freedom. That is, the particle can go in the x direction, it can go in the y direction, or it can go in the z direction. And it can have energy of motion in either one of those 3 ways. So therefore it can have energy in the x, 1/2 mvx squared. It can have energy in the y direction, 1/2 mvy squared. And it can have energy in the z, 1/2 mvz squared. So it's like my banker problem here with my robberies, but now I have 3, not 2 accounts for each molecule. And so it divides up that by 1/3, and that's why it takes 3 times as much energy, why there's a 3 here, to raise this thing for the same amount of temperature change. Diatomic gases. People looked at diatomic gases. And when they looked at diatomic gases, they saw an interesting thing. They saw the 3/2 R that they expected, but as they raised the temperature, they found that the amount of energy they had to give to raise it even further changed. The specific heat, molar specific heat, changed to 5/2 R. And then at another temperature, it in fact went up to 7/2 R. So this is the specific heat per volume, and this is the temperature in Kelvin. Why was that? Why did it change? Well, this is the reason. It turns out there are many ways that the energy can be stored. You have the 3 translations, X, Y, and Z, but you also, in the diatomic molecule, have 2 atoms here, and they can be thought of as connected by a rod. And that means they can rotate. So let's say that we consider this to be the Z direction, this to be along here the X, and this along the Y. So it could be rotating about an axis through the Z, in which case you can have kinetic energy, moment of inertia about the Z axis times how fast it moves around the Z squared over 2. That's just the rotation kinetic energy formula earlier. But it also could, instead of rotating about that axis, it could rotate about an axis through the Y. In which case you'd have a different moment of inertia, a different speed component, again over 2. It cannot rotate about X because all the mass lies along the X-axis. It has no moment of inertia. So there are 2 degrees of freedom there. And then there are 2 more degrees of freedom if you want to consider the fact that it could vibrate. You can think of it as connected by a spring. And these atoms can move symmetrically about some center of mass here that doesn't change. And their energy could be stored as 1/2 k x squared. But they also can move asymmetrically. That is, one of them could move out and the other one move out, or they could move, for instance, like this, where they bend. So there are 2, both the stretching along the axis and about the center mass that can happen. This is called an asymmetric stretch. This is the reason for the different values. We start out with the 3 translational modes, pick up 2 more modes, 2 more. It also, the fact that it falls out at different temperatures is our first example of quantum mechanics, that a certain amount of energy is required for one of these processes to start taking place. This leads to the idea of energy levels. So again, this was neat study because it told us about the microscopic world. And this is long before we ever had the Bohr atom. All right, I'll see you in another video.